pay attention. No, I'm going to. I'm going to say, and you're like, there's a lot of this.
Well, there's just a lot. Hopefully you remember most of this from Algebra 2 pre-calculus, so that it won't be so bad. But there is a couple, especially if you didn't take pre-calculus, we're going to talk about something today that you didn't learn in Algebra 2 pre-cal people. We did learn about it, but we'll see what you remember or not. But a polynomial function is one that can be written like this. It always scares people when I write a polynomial like this. But it basically just means something to some power, and then normally we go down by 1. And so forget about all the letters. That could be like 3x to the fourth plus 7x to the third plus 2x squared plus 4x minus 3. Right? Normally we go down one exponent at a time. And right? So that's what this notation means. N is the highest exponent, and then usually there's no exponent at the end. Be versions of this. Big thing to remember is that the exponent is a non-negative integer. That means no negative exponents, no letters in the denominator, because that's a negative exponent, no fractions, no square root stuff, right? So to be a polynomial, it has to just be like integers, no crazy stuff going on. No crazy stuff. That's how I remember it. So part of your homework today is just given an equation determining if it's a polynomial. Really important to remember that the graph will always be a smooth curve, no sharp corners, right? Normally we think of graphs something like this. That's a polynomial function, or one version of it. It will always be continuous, which means the domain will always be all real numbers because there's no gaps in the graph, there's no jumps, there's no asymptotes, there are no holes in the graph. And eventually, like maybe tomorrow or the next day, we'll graph these by doing a bunch of stuff. Okay, so today is kind of like trying to get you the information so that tomorrow you'll be able to graph these. And I will tell you there's one on your unit test you have to graph. It's like a 10-point question. So 100-point test, 10% of it is this one graph, so you want to make sure that you're able to make a good graph. The degree of a polynomial function is just the largest power of x. So whatever the highest exponent is, that is the degree. We're going to talk a lot about the degree, and maybe you remember from pre-cal or algebra 2, the degree tells us a lot in terms of turning points, in terms of how many zeros it has, in terms of how the arrows behave at the end. All of that is from the degree, so it's really important you can tell me the degree. So the first part of your homework are just like these 3 questions. It says determine if the function is a polynomial. That means no crazy stuff. And if it is a polynomial, tell me the degree. If not, tell me why not. And I'm okay if you just like circle why not, or, you know, a couple words. You don't have to write a paragraph here. So what about this? 2 minus 3x to the fourth. Does that look like no crazy stuff? And there's nothing weird going on. We have a nice exponent there, no fractions in the denominator, no x's in the denominator. So we'll say it is a polynomial, and the degree of this polynomial will be what? 4, because it's just the highest exponent. There's only one exponent, so the degree is 4. That's it. That's an easy question, right? What about number 2? I kind of threw this one in to trick you, which means maybe it's the opposite of what you think the answer is going to be. What do you think about number 2? Is that a polynomial? People want to say no because there's no x in it, right? But it is a polynomial because it could just be, think about, could it be like 3x to the 0? Is that the same as just saying 3? It's a monomial, it's just one thing, but it is a polynomial. A linear function is also a polynomial, it's just degree 0. Oh look, I just gave away the degree here. So this is one of those that's a trick. It is a polynomial, and we're going to say the degree is 0 because there is no x with the power. So don't say 1, because some people argue that it should be 3 to the first power, but the degree is the power on the letter. There is no letter, so that means it's degree 0. What about number 3? Square root is crazy stuff, right? Because think about if you wrote that as a power, that's x to the 1/2 power. Your powers have to be integers, which means no fractions, no decimals, no negative integers even. So no, and you could just say, like you could just circle it, or you can say no, why? Because square root. That's a good enough explanation for me. Why negative exponent? Why x in the denominator? Right? Like just recognizing that you see why you can't have it. Okay. So what we care about is solving polynomial equations. And when we solve something, that means we want to find the zeros of this. So in Algebra 2, I always stress, and Mr. McClure always stressed, because I gave Mr. McClure my notes and he taught what I told him to teach. I'd be like, use these notes, teach this, here's my test, use my test. So I know that he taught you they're the 4 things that are true about zeros of a function. So we can say if you set your function, you plug in a value and you get 0, then it is a real zero of the polynomial function. If it's a 0, that means it is an x-intercept. A x-intercept, maybe I don't need an there. Right? A 0 means it touches the x-axis. We say that the x minus r is a factor of the function, right? Factors and zeros kind of go hand in hand. And we say r is a solution to the equation f of x equals 0. I don't really plan that I'm ever going to ask you to repeat these 4 things, but it's important because I could ask a question 4 different ways. I could say find the solution to this. I could say find the zeros of this. I could say find the x-intercepts of this. I could say find the factors of this function. All of those mean setting that equation equal to 0 and solving it. And so you just have to make sure you're aware that those all mean the same thing. So the real zeros of a polynomial function are the x-intercepts. Is that the right answer here? Are the x-intercepts of the graph and are found by solving the equation f of x equals 0. That's the answer to that sentence. So far? Okay. So what if I gave you 3 zeros of a function? Could you write the function that has those 3 zeros? We just did that on the pre-calc test. All those 4 kids that were finishing the test when you walked in. Remember those days of pre-calc? So if the zeros are x equals -3, x equals 2, and x equals 5, we want to go from the solution back to the factor. So if x equals -3 is the answer, what was it before you solved it? X plus 3. You can just think about moving that back over again equals 0. If it's x equals 2, then it's x minus 2. And if it's x equals 5, then it's x minus 5. Notice it says find a polynomial, which means they want you to actually work this out, right? They want you to multiply that out, which is just a little bit of work to do. You cannot multiply 3 binomials at once. You can only do 2 at a time. So like pick the first 2 and FOIL it out, and then take that answer and multiply again. So you would get x squared minus 2x plus 3x minus 6. I'm going to go ahead and say that's x squared plus x minus 6. So I have less to distribute on the next one. And now this isn't really FOIL, because FOIL you can only do with the binomial and a binomial, but we're going to take everything in the first parenthesis and multiply it to the second parenthesis. Remember, when you multiply, you add exponents. And then we're just going to combine like terms. In pre-calculus, we had a question like this on our last chapter test. And in this chapter test, I threw an imaginary one in, so they have a little bit more work to do. But the biggest thing that happens is people just make little multiplication mistakes, so you just want to try to be careful. Don't multiply or subtract wrong. So that would be x to the third minus 5x squared plus x squared minus 5x minus 6x plus 30. So then we can just combine like terms. Negative 5 plus 1 is negative 4x squared. Negative 5 minus 6 is negative 11x plus 30. And this, notice it is degree 3, would be a polynomial that has those 3 zeros. And so it's kind of like working backwards. I think you have 1 or 2 of those on your homework today. Yes. So then,
What about 1 and 2 zeros? Just like 1/2 if you do automatically fill it.
the 0 can be 1/2. Right? And so there's 2 ways to do that. You could write that as x minus 1/2. Or think about working backwards, like if you were going to, if that was originally equal 0, I like to think about you could multiply by 2 and you'd have 2x equals 1. 2x minus 1 would be the factor that gave you the 0 and 1/2. You see what I'm saying? And so these can be fractions. The exponents can be fractions.
Oh.
Okay? So you can have fractional zeros, you just can't have fractional degrees. Okay? Other questions at all?
Alright, moving on.
Alright, so if you didn't take pre-calculus, then this is a new concept for you. If you did take pre-calculus, maybe you slept since and forgotten. But I graphed both of these on the graphing calculator and I just copied them over. Notice both of them have a 0 at 0, right? They both have a vertex starting at 0, and maybe it's kind of hard to see here, but if you notice what's the difference between these two graphs, one thing you could notice is the x to the 4th kind of goes up at a faster rate, so it looks a little thinner. Agree with that? But what I really want you to notice is what's happening at the x-axis. And if you look at this one, it comes down and it touches and it turns and goes right back up pretty much. But you notice how this one, it kind of almost looks like it hangs around at the x-axis a little bit more. It's flattening out. That's because it has a power of 4. This one has a power of 2. This is the idea called multiplicity, very fancy word, but it basically means the higher the degree, the more that it flattens out on the x-axis. Think about when you do something that just has a power of 1. Like if you solve the equation x minus 1 equals 0, if you graph x minus 1, it just crosses at 1 and it goes straight through. It doesn't flatten out at all. That's because it doesn't have a power there. But when you add powers to it, it causes it to flatten out more. And so we want to talk about what multiplicity does to our graph. And I can tell you for sure on the unit test, the one that you have to graph is worth 10 points. There are some zeros that have a multiplicity, so you have to start being aware of how that affects what your graph looks like. And tomorrow we'll graph those, or maybe whatever the next day would be, Thursday. I don't know how much time he's going to talk about our quiz. But today you just have to recognize multiplicity. It's really easy to recognize because it's just a power. So if you have some factor written as a power, if that is a factor of a polynomial, then r is the 0 and the multiplicity is just whatever the exponent is. So it's nothing fancy. You don't have to do a lot of work to find it. You just have to recognize if there's a power out there, then it has a multiplicity, which means it's going to change what your graph looks like. If your graph has an even multiplicity, like those two graphs we just looked at, then at that 0, then the graph of f will just touch, and we should say touches for grammatically correct reasons there, the graph of f touches the x-axis. So like it's just going to touch like that. That's a quadratic. But you could also have an odd multiplicity, like if it was to the 3rd power or the 5th power. And if you have an odd multiplicity, then the graph of your function will always cross or crosses the x-axis. Think about x to the 3rd. X to the 3rd comes up and it kind of flattens out a little bit and then turns like that. That's odd, so that's why it crosses. And because it has a multiplicity of 3, that's why it kind of flattens out there. Today you're just going to tell me what is the 0 and what its multiplicity is, and then we'll get to graphing later. Questions about that idea of multiplicity before we do some examples? Okay. So this is what you're going to see. It says state the multiplicity of each 0 of the function and state whether the 0 crosses or touches. When we start graphing these, we get to start with that. What are my zeros? What is its multiplicity? Does it cross? Does it touch? Because that's going to help you make a nice, accurate graph. So the nice thing is you don't have to do any work, right? What is the 0 here? What's going to make this go to 0? 4. So I can say the 0 is x equals 4. Its multiplicity is, what is the power out here? So I just say multiplicity 2. And then you just have to know, because it has an even multiplicity, does it touch the x-axis there or does it cross the x-axis? Touches. It might seem silly right now just to write all that, but think about when you're making a graph, that's going to change what your graph looks like. Instead of having to pick like 78 points to graph it, if you know this information, it's going to help you make a really accurate graph without making a giant XY chart. What about this one? What would the 0 of this be? What makes this go to 0? Negative 1. What's its multiplicity? 3. And since that's an odd number, does it touch or does it cross? What about x plus 3? So that would be -3. And so let's have a talk about this. Some people want to tell me that it has a multiplicity of 1, but when you multiply something by 1, does it change? If you multiply any number by 1, it stays the same, right? Do you agree with that? No, you're right. I'm with you. So since it has a power of 1 and 1 doesn't change anything, we actually say this has no multiplicity. That way you don't think about it changing on the graph. It's not going to change, it's just going to go straight through. So I'm going to say no multiplicity and just try to check that. In pre-cal, when we talk about this, is always a big, people want to say 1 there. But we still, multiplicity. That would be if it was just a number and not an x. You see what I'm saying? Like, because this actually does have a power of 1 there, it still counts as a 0. And we can still say that it crosses because we know any 0 that's just like, think about a linear line anytime it touches the x-axis, it is still going to cross because it's an odd number, but it's just not going to flatten out. It's not going to change any. All right? Questions about those answers there? All right, I got 2 more things for you. Rules kind of for you, and then we're going to do a couple examples. And we're just flying through this because I think I'll do that for you. Okay, this one's pretty easy, and again, it's going to help you on your homework today. There's going to be like parts like A, B, C, D, and one of the parts is going to say what is the maximum number of turning points. This is not something I think a lot about, but it's something that's very important when you're making a graph. How do you know if it turns again without picking a million points? Is if you have a polynomial function of degree n, then the graph has at most n minus 1 turning points. That means whatever the degree is, the number of times that it can turn or have like a maximum and min is 1 less than that degree. And the easiest example for me to think of is one graph that we know. We know what x squared looks like, right? What is the degree of x squared? How many times does any quadratic function ever turn? It only has a maximum or minimum. Like, it's never going to turn and then come back down when it's a quadratic. That's true for any polynomial. If you had a degree 5 polynomial, you know the most times it's going to turn is 1 less than that is 4. It could be less than that, but the most it would be is 1 less than that. And so sometimes if I gave you a graph, if I gave you this graph and I said, what's the biggest degree this could be, what would you tell me? Because it turns 1, 2, 3 times, the highest degree this could be is degree 4. The lowest degree this could be is degree 4. That's not necessary. Because it could be like degree 7, but only have 3 turning points. But it has to be at least a degree 4 because it has 3 turning points. And so that's the idea behind this. It's also when we start making graphs, it helps you from having to pick a ton of points if you can check the number of turning points. All right, so it's just one of those things that we'll review as we go through this. Now the next thing, if you took my class for pre-calculus, we have this exact same slide. I copy and pasted it because it's very useful for me. I think Mr. McClure used this same slide in Algebra 2, but I don't know. We'll see. The other important thing we need to know before we graph polynomials is which way the arrows go. And this kind of looks a little scary, but basically you can tell which way the arrows go based on the degree and the leading coefficient. And so notice I wrote this out, that my degree is n. So when I talk about n here, that means my degree. If you think you're going to forget that, maybe you should write when degree is odd, when degree is even. And I know you did this in Algebra 2, I just don't know how it was presented to you. But even functions, the arrows go in the same direction. They either both point up or they both point down. Odd degree functions, the arrows go in opposite directions. So I like to pretend we're dancing here. Okay. How do you know which way it is? Is it both up? Is it both down? Is it like this or is it like this? You look at the degree and you look at the leading coefficient. The leading coefficient is the number in front of the highest degree. So in my little polynomial up here, the leading coefficient would be a sub n. And if your degree is odd, your arrows are going to go in opposite directions. And if your leading coefficient is positive, think about your graph, right? If this was your graph, if it's odd, the positive side of your graph is going to go up, the negative side of your graph is going to go down, and then anything could happen in the middle depending on what the degree is and what the zeros are. But your arrows should end with the right side going up and the left side going down. We can write this out real fancy. I don't. Sometimes when you teach something in 3 different classes, it's hard to remember how everybody wants to know these. There's algebra 1, algebra 2 we do this, pre-cal we do this, and in this class we do this. Yeah, they write it like this too. I don't know that they actually make it describe showing the end behavior. Okay. So if they ask you to find the end behavior, it's really nice to write it out in nice terms. We say, what's happening as x getting bigger? So we say, as x goes to infinity, what's happening to my graph? My graph is the y part, and we would say, as x is getting bigger, y is getting bigger, right? As x goes up, y goes up. And as x is getting smaller, or we can say as x goes to negative infinity, what's happening to my graph on this one? Then my graph is also getting smaller. Vague memories of writing that out in algebra 2 class. Really, the notation is the same, except for each time you go through and you change what's happening on the y's. So after you do this a few times, it's going to get a little easier to do. I find the picture helps me a lot. If your leading coefficient is negative, then they switch. So I've always remembered this. If it's odd, positive goes up, negative goes down. That makes sense to me. But if the leading coefficient is negative, then it flips over. So again, if we draw a picture here, that now means the negative side is going to go up and the positive side is going to go down. And every time you're writing this out as the notation, this is what you write. As x goes to infinity, f of x goes to something. As x goes to negative infinity, f of x goes to something. And then all you have to do is think about which way are your arrows going. The positive side is now pointing down, so this is now going to negative infinity. And the negative side is now going up, so it's going to go to positive infinity. When your degree is odd, they will always be different because they go in opposite directions. When your degree is even, think about x squared. They always either both point up or they both point down. If your leading coefficient is positive, think about x squared. It points up. So that would mean like both arrows, well, like field goal. So on this one, since they both go up, my end answers are infinity, infinity. And think about negative x squared, they flip over, so they both point down. So if you draw the picture, it's like both pointing down towards negative infinity. And again, I don't think very often in this class do you actually have to write the infinity stuff, but when we graph these, this is super helpful to know which way the arrows end. It saves you from picking a lot of points. It also lets you check to see if your answer makes sense. All right, they're both pointing down. Does my graph both point down? No. Okay, I did something wrong. But these are both going to point to negative infinity. So on your homework today, you're going to first determine is something a polynomial, give the degree. I'm going to give you the zeros, you're going to write the polynomial. And then the last couple 3 questions are using these tests. And so I copied the directions that you're going to be doing on your homework. And so it says for each polynomial function, a, b, c, and d. Part A, list each real zero and its multiplicity. Determine whether the graph crosses or touches, right? We did that all in one thing earlier, but now it's parts A and B. Part C, determine the maximum number of turning points. That's based on the degree. Part D, determine the end behavior. That's based on the degree and the leading coefficient. So there's not really a lot of work to show here today. It's just checking to see, do you understand these rules before we start graphing them. All right, so the good news is you don't have to graph today, and it's not a lot of work to show, but it's just making sure you do all parts. Nice thing is, again, it's all factored for us. So list each zero. Is this going to be a 0? There's no x here with this 3, right? So don't let that throw you. 3 cannot equal 0, so that's not a 0. What about this? Can there be a 0 here? What's going to make that go to 0? X equals 7. What about this one? Is there a 0 here? What makes that go to 0? Negative 3. List each 0 and its multiplicity. X minus 7, what's multiplicity? None. There's no power out here. If there's none, you don't even have to say it. But if you want to, you can say no multiplicity. What about negative 3? What's its multiplicity? The multiplicity is the power on the outside, so this one has a multiplicity of 2. That is part A. Part B, determine whether the graph crosses or touches at each x-intercept. I would just go right underneath here and say, well, there's no multiplicity, but since it's like a power of 1, is that going to cross or touch? Cross. Odd crosses, even touches, which means this one touches. And if you write it right underneath there, I'll know it goes right with it. You don't have to restate at 7, it crosses. At negative 3, it touches. Just like we did on our other example. Part C, determine the maximum number of turning points. So you do have to think a little bit about this. You have to think what the degree would be if you multiplied all this out. You do not have to multiply it all out, but you do need to think about what the highest exponent would be. If you FOILed this out, x plus 3 times x plus 3, do you agree we would get an x squared out of that? Follow me on that? And then if I take x squared times x, would I be at x to the third? So x times x squared, I would have an x to the third. So you do have to think about what you would get if you multiplied it all together. You shouldn't have to multiply it all out to get that the degree is 3, which means how many turning points could this have? 1 less than that. So that's it. It's just 2. You don't have to write anything else down, but you have to think about what the degree would be. And then D, determine the end behavior. We already know it's an odd because it's x to the third. You do need to make sure you pay attention. This is just a 3 in front here, so our leading term would be 3. So if you forgot that, not a big deal. But if that would have been a negative number, that changes things, right? So it's odd and positive. You need to make sure you learn these rules. But odd and positive, they go in opposite directions. That means the negative side goes down, the positive side goes up. But probably we should actually write it out. As x goes to infinity, f of x is also going to go to infinity. And as x goes to negative infinity, f of x goes to negative infinity. Well, because we're fancy. It's the same thing. So I guess if you put y, I wouldn't mark it wrong. We're just saying it's a function. Okay, so there's one more on here. I want you to do the same A, B, C, and D, and do number 7. That is x plus 1/2. So don't freak out too much about that. You don't have to FOIL it all out. But see if you can determine the zeros, the multiplicity, crosses or touches, number of turning points, and end behavior, and we'll see if we're good to go. However it makes sense. Well, because if you know this, and if it's just x, you'll know you just multiply by 1. You see what I'm saying? So there's not going to be another derivative quiz that you just have to memorize things. So if this makes more sense to you, just do this. And so on the front, if you just want to write even u, you see what I'm saying? Is it fine? Yeah, okay. whether the number on the outside is even or odd. So that. There's a question on your unit exam that gives you a big giant polynomial with a bunch of zeros and a bunch of powers, and you have to write down all the zeros and all the multiplicities, and whether they cross or touch. You know, not bad. The one you grab is pretty terrible, I'm not gonna lie. Definitely not one I would have picked to put on an exam. The one on the exam that you have to grab. Yeah, it's just super big numbers, and so they don't label the y-axis because they want you to just label it, but so like, you get like a giant number like 7,000 or something, and you have to just label your y-axis accordingly.
Well, at least we know it's going to be a big number now.
Oh yeah.
I think I always try to most of the part, I was like, good. And you're like, nope, not fast enough.
Alright, so if it's 1/2, then that means the zero's at -1/2. And if it's x plus 4, if I set that equal to 0, I would get -4. Multiplicity is just a number on the outside. So this one has a multiplicity of 2, this one has a multiplicity of 3. Touches or crosses is based on even or odd. Even, think about x squared. Touches, odd, think about x cubed. Crosses. Questions about that? That's A and B. Number of turning points. Again, you have to think about if you worked all this out. I just always kind of look at the powers, right? Like if there's a 2 out here, I know I'm going to end up with an x squared here. If there's a 3 out here, I'm going to end up taking x times x times x at some point. So I'm going to get x to the 3rd. And when you multiply, you add the exponents, which means you're going to end up with a 5th degree on this one. You agree with that? So if that's 5th degree, what's the answer to part C? 4, 1 less. No, when you multiply, you add though, right? Crazy math. Okay. And then the in behavior, be careful on this because you might just say, oh, x to the 5th, it's just like number 6, but I threw that -2 in there, that if you multiplied all that out, at the end, you'd end up multiplying this by -2. So it actually has a negative leading coefficient, so it's going to be the opposite of number 6. Now this side's going to go up, and this side's going to go down because it's odd and a negative leading coefficient. So we would say as x goes to infinity, f of x is going to go to -infinity, and as x goes to -infinity, f of x goes to infinity. Study that chart, learn that chart, because you need to know which way the arrows go. Questions about that? So that's kind of like a whole lot of polynomial review without graphing. And then the one thing left, like spending 2 days on this section, is tomorrow is the graphing part of this section. So, this is on your paper that I didn't want to waste finish your paper, I think. 15 through 21 multiples of 3, that's only 3 problems, and it's just, is it a polynomial? State the degree, just like our first 3 examples. 42 is write the polynomial given the zeros, just like our next example. And then 51, 54, and 59 are just like the 2 we did, except you're going to skip part C because they talk about what happens. I don't even know. It's just a weird question that we're not answering, so just don't do part C, but I think it's like parts A, B, D, and E maybe. And then 65 is a question with the graph, and we'll talk about tomorrow if we have questions about it, but I just want to give you that one to think about. And then tomorrow we'll do graphing, hopefully. We'll also talk about the quizzes tomorrow. I didn't make the chart because, you know, Olivia could make the wall of fame still. Right. Well, okay. But it was out of 35 points, and 33 out of 35 was the high score. Nick Chambers. And so the bad thing about only being out of 35 points is it doesn't take long for it to go to a B, right? And so then 31 out of 35 is a B+. And Jake Berg and Bobby got that next high score. Oh wait, just kidding. It would be